Today, let's talk about heat changes in chemical processes. That is, determination of enthalpy change. Let's look at determination of enthalpy change. So this is considered under enthalpy of neutralization, enthalpy of combustion, enthalpy of displacement, enthalpy of solution and dissolution, Now, let us start by talking about enthalpy of combustion. Experiment that has the following procedure. Pour exactly 100 cubic centimeters of distilled water in a 250 ml glass beaker. Record the temperature of water. Half fill a small bottle with ethanol and close it tightly with a lid fitted with a clean wick. Weigh the bottle and its contents and arrange the apparatus as shown below. Light the wick to start heating the water. Stir the water carefully with the thermometer and extinguish the flame when the temperature of water has risen by 1.5 degrees Celsius. Weigh the bottle and its contents again. Record the results obtained. Observation and explanation will be from that experiment. Now, from that experimental procedure, this is how we are going to have the heating taking place. Now, there is a diagram where the water is being heated as shown in that diagram. Now, what is the experimental procedure and observation? This is heating taking place. There is a wick there. Observations and explanation. Initial mass of the bottle with this content is W1. Mass of bottle, that is W1, which is 84.8 grams. Then final mass of ethanol band is equals to, first of all, we'll have to know the final mass of the bottle. Final mass of the bottle, which is, we may call W2, and that is 83.1 grams. Therefore, mass of ethanol band will be W1 minus W2, that is simply 84.8 minus 83.1, and that gives 1.7 grams. Final temperature of water, that is another observation that was recorded. Is equals to 43 degrees Celsius, and that is level T2. Initial temperature of water is equals to 28 degrees Celsius, and that is T1, meaning change in temperature, that is delta T, is T T2, the final one, minus T1, and that gives a difference of simply 28 subtracted from 43, and that is exactly 15 degrees Celsius. Good. Now, these are the results that we have from the experiment that was done, that is by recording temperature after the heating of water using ethanol, simply combustion of ethanol from the experiment. And during that, we are trying to note the temperature and also knowing the mass of ethanol that is burnt. Now, this is now the result that is obtained. That is the thermometer that will help us to know the temperature. That is ethanol in the bottle. We have a wick inside, then thin copper container having the water being heated. Now, in determining the heat produced when ethanol burned, a known mass of ethanol is used, and the heat produced is used to raise the temperature of a known mass of water. Now, to determine the exact heat of combustion of any substance, it is important to have knowledge of heat capacities of the materials used in constructing the apparatus used in such experiments. That's why we realize that the values that are calculated theoretically, or rather, the ones that are calculated from the experiments, are usually lower than the expected theoretical values, because there is some aspect of heat loss. Let's try to calculate the molar heat of combustion of the 17 grams, of the 1.7 grams of ethanol that we've obtained from this experiment. And that will start directly from knowing the delta H, the heat change. Then after knowing the heat change, we'll now go ahead and determine the molar heat of combustion. Now, we have realized that delta H is 15 degrees Celsius. Volume of water that was used is 100 degrees Celsius. 100 cubic centimeters. It is temperature that is in degrees Celsius. Sorry for that. Now, from there, we know that mass is equals to density times volume. And density of water is 1 gram per cubic centimeters. So mass of water, this implies that mass of water is equals to 100 times 1, which is 100 grams. Now, let's determine enthalpy change. enthalpy change delta H is equals to mc delta T, where m is the mass, c is the specific heat capacity, that is normally 4.2 joules per grams per Kelvin, or 4.2 kilojoule per kilogram per Kelvin. So the use of 4.2 will be controlled by the grams. If you want it in kilojoule, then we must use the kilogram. If you want it in joules, then we'll have to use the grams. Therefore, a delta H during combustion of ethanol will be the mass, that is 100 grams multiplied by 4.2 joules per grams per Kelvin times change in temperature, that is 15 Kelvin. The change in temperature is either in Kelvin or degrees Celsius, and that's why we don't need to do the conversion from degrees Celsius to Kelvin. It's simply a change. Now that cancels that with that, so we have 100 times 4.2 times 15. What will that give us? So we have 100 times 4.2 times 15, and that gives 6,300 joules. In kilojoule, we'll just divide by 1000 so that we have 6.3 kilojoule. This amount of heat is produced by 1.7 grams of ethanol. We can go ahead and calculate now the molar heat of combustion. Let's have the two ways of calculating molar heat of combustion. Alternative 1 will say if 1.7 grams is able to produce 6.3 kilojoule, that is the amount of heat, what about the 46 grams in 1 mole? The 46 grams, that is the molar mass of ethanol, CH2OH. If you sum up, you get 46. So that gives 46 grams times 6.3 kilojoule over 1.7. And that will eventually give 170.47 kilojoule per mole. Alternatively, we can first calculate the moles, number of moles. Recall that mole is equals to mass over molar mass. That is 1.7 divided by 46 as the molar mass, that is grams per mole. That and that vanishes, so we have 1.7 divided by 46, that gives 0.03696 mole. So this implies that it is 0.03696 mole that produces 6.3 kilojoule. What about 1 mole? So that is 1 times 6.3 kilojoule divided by 0.03696 mole. That eventually gives, that is 6.3 divided by that, we're getting 170.47 kilojoule per mole. So we have two options that we can use to calculate the same. So that is how we can calculate the molar heat of combustion of the ethanol that was used during that experiment. And molar heat of combustion, there is a heat that is absorbed, and that is why molar heat of combustion has to be given that sign. Now, I want us to look at some other examples. So that is negative delta. We have looked at the release. So to put that an equation, before we look at some other examples, we shall have the thermochemical equation as follows. CH3 CH2OH, liquid undergoing combustion, and that gives CO3 and water, CO2 and water. This is gaseous, liquid, 3, 2. Delta H is equals to minus 170.47 kilojoule per mole. That is the thermochemical equation. This thermochemical equation can be illustrated in the energy level diagram as follows. So we can have energy level diagram for that. That is the y-axis, x-axis, reaction path, or progress. Then there is energy in kilojoule per mole. Well, so we have the reactants at higher level because heat is lost or released. So that is the reactant. Then there is activation energy involved for that. Then we have the products. So products is carbon dioxide gaseous plus water. The delta H for that is negative 170.47 kilojoule per mole. Then there is activation energy. The reactants is simply 1 mole of ethanol undergoing the combustion. That is 3 moles of oxygen used. And that is the illustration of the equation in the energy level diagram. That is the thermochemical equation. Molar heat of combustion, that is the definition now. Molar heat of combustion is the enthalpy change that occurs when 1 mole of a substance is completely burned in oxygen. That is what we call molar heat of combustion. 1 mole. And that is why it has to be per mole. That is all about molar heat of combustion that we have used ethanol as an example. We can also have some other questions under the same, still to try to answer the molar heat of combustion questions under different areas, not necessarily ethanol. For example, other examples sulfur dioxide reacts completely with 1 mole of oxygen. To form sulfur 6 oxide and liberating 1.85 kilojoule of energy. A. Write down the equation for the reaction showing delta H. That is, the equation is as follows. Delta H is equals to negative 1.85 kilojoule. To balance the equation, there is that. Part B, what is the heat of combustion when 1 mole of sulfur dioxide is converted to sulfur 6 oxide in excess oxygen. So now that is 2 moles from that equation gives 1.85 kilojoule watt of 1 mole. So that is 1 times 1.85 divided by 2, that gives 0.925 kilojoule per mole. Another question, that is part C. What would be the heat evolved if only 0.2 mole of sulfur 6 oxide was formed? Now, if now 2 moles formed gives, that is, requires 1.585 kilojoule, what of if we require 0.2 moles? So that is 0.2 times 1.85 divided by 2, and that gives 0.185 kilojoule. So that is what would be required if at all we are calling for 0.2 moles being produced. Another question, that is number 2, which is our last question. .26 grams of element Q was completely burnt in air the heat was used to heat, the amount of heat used to heat 250 cubic centimeters of water, raising the temperature of water, raising the temperature to 32 degrees Celsius, or simply from 32 to 50 degrees Celsius. Calculate the relative atomic mass of element Q. Given that the molar enthalpy of combustion is negative 360 kilojoule per mole. In bracket, density of water is 1 grams per cubic centimeters, and the C to be used is 4.2 kilojoule per kilogram per Kelvin. Solution. Now we are given mass to be 1.26, that is mass of element Q. So our solution mass is equals to 1.26 grams. Heat of combustion will be 0.25 kilogram multiplied by 4.2 kilojoule times 18 Kelvin divided by kilogram times Kelvin. That and that cancels, that and that cancel as well. So we have 18.9 kilojoule. If 360 kilojoule requires 1 mole, we are given that is 360 kilojoule per mole requires 1 mole. How many moles will be there for 18.9 kilojoules? So that will give us how many moles? So that is 18.9 times 1 mole all over 360, and that gives 0.0525 moles. We continue. So now recall RAM, that is relative atomic mass, will be mass over moles, giving 1.26 over the moles, that is 0.0525, and that eventually gives, if we divide well, we get 1.26 divided by 0.0525, exactly 24 grams. So RAM is equals to 24. And that is all about the questions under molar heat of combustion.